Hi, in this video we're going to start talking about logistic regression. It's a very common and a very useful set of analysis tools. Many real problems have data that follow this kind of a form, so it's a very important thing to learn. The crucial thing about logistic regression is to understand that the response variable is going to be different than it's been in any of our other regression situations. The response variable here is going to be a yes or a no. It's not going to be a quantitative variable anymore. It's going to be of the nature y, that there's a variable that takes on a success or a failure, an event happens or it doesn't happen, and we can denote that y equals 1 for the case when the event happens and y equals 0 for when it doesn't happen. A Bernoulli variable is this kind of 0-1 variable, and what it means is that the typical value, the average value of a response variable like this is the parameter theta, where theta is just the probability that the event happens. It's simply a probability. The variation of a Bernoulli variable involves the probability theta as well, and so you can notice here that the typical value of the variable and the variance of the variable are functions of each other, or in other words, the variance is a function of the mean. Notice that the variation becomes a maximum when theta is equal to a half. And from these 0-1 variables, we can make a binomial variable, which is just the sum of these 0-1 variables, all of them added up. And a binomial variable, remember from your intro class, has a typical value that is the number of trials, in this case m, times the probability of an event on any trial, which is theta. In your other classes that might have been called n times p. It's the number of trials times the probability of an event on any trial. The variation of a binomial variable is m times the probability times 1 minus the probability. Notice again here that the variation is a function of the mean. It's a function of m theta, just as we've defined the mean right there. And so what we're going to do now is connect the probability of an event to predictors or to regressors, x. And so we're going to express the probability parameter theta as a function of beta parameters and x, and the beta transpose x here is called a linear predictor. This is our usual linear combination of beta naught plus beta 1 times x1 plus beta 2 times x2 and so forth. It's just that linear combination that we keep seeing in the mean function of all of our models. And this is really the connection between our predictors and the chance that an event happens. In particular, the explicit function is given right here on the bottom. The probability that an event will happen for subjects or units that have characteristics x is e to the linear to this linear combination beta transpose x over 1 plus e to the beta transpose x. And so here are the predictor characteristics, and they combine in this way to make the probability of an event. So this is what's called the logistic kernel. It's the connection between the probability of the event happening and our characteristics. You can re-express this function in terms of the linear predictor so that you can get the linear combination beta naught plus beta 1 times x1. All of that stuff can be expressed as the log of this fraction. And we haven't really ever probably talked about this kind of fraction before, but inside the parentheses here is a probability of the event happening divided by the probability the event doesn't happen. And that's the definition of an odds. And so this expression right here in the middle of the overhead is the log, the natural log, base e, the log of the odds of the event, not really the probability of the event, but the odds of the event are equal to this linear combination of parameters and data. Now, we haven't probably dealt with odds very much, but you can think about odds just like you can think of probability. When the probability of the event is higher, theta, of course this whole fraction is bigger. When the odds or the chance of the event is smaller, this numerator is smaller and the denominator is bigger, and so the whole fraction becomes smaller when the chance is smaller. So you can think of odds like risk, and it works the same and it moves the same direction as chance or probability. Higher probability means higher odds. Lower probability means lower odds. And I think that's probably good enough for the material that we're doing. Notice that when we're doing something like a coin flip where the event is just as likely to happen as it is not to happen, the fraction here is a half divided by a half, which is 1, and that is the odds for an even event. And so finally we get to define the logistic regression model, and we define it in terms of the odds of the event. Y equals 1 means the event happens. The odds that the event happens for characteristics x1 to xp is e raised to the beta naught plus beta 1 x1 up to beta p xp. So e raised to this linear function controls the risk. When the risk or the odds of the event is higher, it must mean that this linear function is accumulating bigger values. If the risk is lower and it's not a very likely event, then this linear combination is adding up smaller and smaller values. Remember that if this linear combination takes on very negative values, you will have e to a very big negative number, and that starts to get you close to 0. If you have this linear function to be very big numbers, arbitrarily large, this will be e to a very large number and can go off to infinity. So in other words, odds can get as big as infinity and as small as 0. And so the data for this kind of problem will consist of the event indicators y and the number of trials for that set of predictor values. A very common situation is that every individual unit has its own set of predictor values, and that would mean that the repeating amount mi is 1, and the y variable would either be a 0 or a 1, depending on if the event happened or it didn't happen. Let's take a look at the most simple case of a logistic regression model, a one predictor model that has the notation x. The probability that the event happens is this expression. The odds that the event happens is the probability that the event happens divided by it doesn't happen. That's the odds. And the model is that it's e to the beta naught plus beta 1 times x. And so what controls the relationship between risk of the event and the predictor is the parameter beta 1. Beta 1 is the controlling parameter that controls whether there is a connection between the predictor x and the response variable, the event variable y. It controls everything. Beta naught is really not of any interest. It just keeps track of overall how risky is the event generally, and it's usually not something of any interest. Let's take a look at a particular kind of single predictor, one that is two groups. So x equals 1 means that an individual is in a particular group, and x equals 0 means it's in another group. Could be something like males and females. And so what we're doing here is we are constructing a ratio of risk or a ratio of odds. OR means odds ratio. What's the risk of the event for someone that's in the numerator group, say males, divided by the risk of the event for someone that is in the denominator group, say females. And remember that the logistic regression model is specified through these odds right here, and so we have e to the beta naught plus beta 1 times x, and we plug that in for the value of x equals 1, and so we will have e to the beta naught plus beta 1 times 1, and that's where this numerator came from, e to the beta naught plus beta 1 times 1. For the denominator group, remember the value of x is 0, so that when you plug in the odds function for the denominator, you get e to the beta naught plus beta 1 times 0, which wipes out the beta 1, and that's why we are left with e to the beta naught down here. We have e to the beta naught times e to the beta 1, and an e to the beta naught down here in the denominator, and the e to the beta naughts cancel. This is a exponent with a common base, and you add exponents together when they're a product. This is equivalent to e to the beta naught times e to the beta 1. With a multiple with a common base, the exponents add, and that's why I expressed it this way. Point is that the beta naughts cancel, and you're left with e to the beta 1. And so the relative risk, or the odds ratio, depends on the parameter beta 1. It controls the whole story. If there really is no difference between the groups, group x equals 1 is the same risk, same chance as x equals 0, it will mean that the numerator odds is the same as the denominator odds, and that means the odds ratio will be 1. And the only way you can have an odds ratio of 1 is e to the 0. E to the 0 will give a result of 1. So beta 1 being 0 is the same as no difference in risk between the two groups. If the numerator group has more probability or more risk of the event, it'll mean the numerator is bigger than the denominator. If there's higher odds or higher risk, the numerator will be bigger than the denominator, and this fraction will be bigger than 1. And the only way that can happen is if beta 1 is greater than 0. It's a positive number. If the numerator group has less risk of the event, it has got to mean that this odds ratio is less than 1. And the only way that can happen is if the beta 1 parameter is a negative number. So beta 1 controls the change. Here is an example of illustrating this. It's data from ratemyprofessor.com, and the outcome variable is whether the particular faculty member has been thought of by their students as physically attractive, and if the students think the faculty member is attractive, they are given a pepper rating, yes or no. Pepper yes means the professor is attractive. Pepper no means they weren't considered attractive by that student. And so that's the event variable y, and the predictor variable x is the gender of the faculty member. Is the gender, and the gender of the faculty member could be either male or female. And in this case, x equals 1 signifies a male faculty member, x equals 0 signifies a female faculty member. And so this is the basic expression of a logistic regression model. It's a little bit different because we use the GLM function and not the LM function. The response variable is over here like it always is. The predictor is over here. You specify logistic regression through the family equals binomial option. This is what controls whether it's logistic regression or not. And then the data frame is rate prof. Here's the summary of the model, and I want you to notice right down here that the estimated coefficient for the gender variable is a negative number. And that means something about which group has higher or lower risk of getting a pepper rating. So remember, e to the beta coefficient controls the odds ratio. And so in this case, I'm taking e to the coefficients of that model. Here is the beta 1 hat coefficient for gender, and e to the beta 1 hat is our estimate of the odds ratio of getting a pepper rating for a male faculty member divided by the odds of getting a pepper rating for a female faculty member. And this fraction, you'll notice, is less than 1, signifying that males have less probability or less risk of getting a attractiveness rating compared to female faculty. It's 74% of the risk. The interpretation is right up here. Male faculty member getting a pepper rating is 0.739 times that, whatever the risk is, of a female faculty member. And so since this is a multiple that's less than 1, it's less risk. Notice that if you make a confidence interval for that beta parameter, the confidence interval contains 0, and so there's really not enough evidence to suggest that the underlying beta 1 parameter differs from 0. Or in other words, there's really not enough evidence to say that male or female faculty members get a different risk of a pepper rating. And that would be a simple example of what we're talking about. Another example might be when our predictor variable is a quantitative predictor variable, temperature, blood pressure, something that would be a continuous predictor. Our odds, our logistic regression model, is the same as before, e to the beta naught plus beta 1 times x. X here is a quantitative variable now. And so if you want to communicate what is happening, it's going to be controlled by beta 1. When the values of x go up, when beta 1 is a positive number, it's going to mean the risk of the event goes up when x goes up. If beta 1 is a negative number, it means the risk of the event is going to go down when x variable goes up. And we usually communicate effects with odds ratios. So notice what we've done here in this overhead here, overhead 14. We've presented the odds of the event happening at level x plus 1 of the predictor divided by the odds of the event happening at level x, just 1 unit lower relative, or the numerator is 1 unit higher compared to whatever is in the denominator. Plug into this odds function, the logistic regression model, and you have e to the beta naught plus beta 1 times the predictor value x plus 1. In the denominator, it's times predictor value of x. The beta naught terms cancel in the numerator and denominator. Beta 1 times x cancels with the denominator beta 1 times x, and you're left with a beta 1 times 1 in the numerator. And so this is the relative risk. How much additional risk do you get of the event when the predictor goes up by 1 unit? When beta 1 is a positive number, of course, it means the risk goes up. When beta 1 is negative, it means the risk goes down. Sometimes, though, you might want to talk about an effect not in terms of 1 more unit of x, but maybe 20 more units of x. And in this case, you'd put in x plus 20, everything would cancel out, and you'd be left with an e to the 20 times beta 1, like I'm showing right here. So if you want to compare 20 units more of a predictor compared to a base level, the odds ratio becomes like this. Here's an example using a quantitative predictor. In 1999, there was a severe storm in a wilderness area in northern Minnesota, and we're keeping track of whether trees were blown over and destroyed in the wind, and that's the response variable. And the predictor variable that we're going to use here is the quantitative variable diameter. And so we're going to consider a model. Tree died, yes or no. The odds that the tree died is this logistic function, e to the beta naught plus beta 1 times the log of the diameter, where the diameter d is the tree diameter, how big around the base of the tree is. And so here is how we're going to construct this particular model. This is a little bit of an unusual data situation. For every row of the data frame, for every diameter, we know how many died and how many didn't die. And so this is a combination variable which you will not see very frequently, but it is used in this example. This is just keeping track of the events and the non-events, but you specify it the same way. GLM is a function of the response variable package in this case and the log of diameter. And when we look at the summary, you can see that the log of diameter is a positive number. It means that as the trees get bigger and they catch more of the wind, they're more likely to get blown over and crack and die. Notice it is a very significant effect. So the output shows very clear evidence that the beta 1 parameter that generated these data, there's an association between death and the diameter. One more unit in log diameter would be e to the 3.26, which is 26 times the risk for one log unit smaller. That's an enormous increase in risk. We learned how to talk about increases in log variables, and so you could use that information that you learned earlier in the course from chapter 4. If you increase the diameter by 10%, it means the odds changes by a multiple of log of that times the estimated coefficient. So a 10% increase in the diameter gives a multiple of 1.365 times the additional odds of death. And this is an expansion above 1. It's like a 36% expansion. So it's a greatly increased risk of death. Here's a plot showing the diameter of the trees and the risk of death, and you can see that as the diameter of the tree goes up, the estimated mean function gets very close to 1. If it's a big enough tree, it's almost certainly to have been blown over. Notice on that figure that the diameter was in log scale. The plot symbols there were proportional to how much data there was for that diameter. Larger circles had more data and more weight to estimate parameters. And the solid line that was in that graph is the model prediction. You can take a look at the commands that made this file on our Moodle site just below these overheads. Now we're going to move on and talk about a model that's got 2 factor variables in it, 2 grouping variables. This would be an example like one variable being sex and the other variable, predictor variable, being smoking status. Yes, no. So 2 grouping variables, one of them is x1, one of them is x2. Our logistic regression model expresses the connection between the risk or odds of the event and the predictors like this. If we wanted to talk about the effect of x1 controlling for x2, we'd have the odds of the event happening for x1 is 1 divided by the odds for x1 is 0, and the value of x2 would be held constant between the 2 cases in numerator and denominator. We would plug into our odds function x1 equals 1 in the numerator, x1 equals 0 for the denominator. x2 would be just a value denoted by x2, and it would appear in both the numerator and denominator. And when you would cancel common terms, the beta naught and the beta 2x2, you're left with an e to the beta 1. And so notice that in this kind of model, the effect of x1 x1 does not really depend on the level of x2, but it does depend on the fact that x2 is in the model to estimate this effect. So make sure you pay attention to the bottom of this overhead. You would interpret beta 1 as the change in the log of the odds. If you take the log of this, you'd get the log of the odds going from x1 of 0 to x1 of 1 after adjusting for x2. When a predictor has more than 2 levels, let's just say k of them, you need k minus 1 indicator variables to fully specify that information. You've seen this before when we've dealt with factor variables earlier in the course in models that have factors. For example, if we've got k equals 3, a logistic model could be specified like this. We would have e to the beta naught plus beta 1 x1 plus beta 2 x2. X1 would be an indicator variable if somebody's in the first group, and 0 if it isn't, and x2 would be equal to 1 if someone was in the second group, and 0 if they weren't. And that means that in the model, the third group is left out. So if you wanted to compare the odds of somebody having the event in group 1 compared to having the event in group 3, you specify your odds function, e to the beta naught plus beta 1 times 1, because they're in group 1, and then it would be plus beta 2 times 0, because if someone is in group 1 in the numerator, they can't be in group 2, so the indicator x2 for group 2 would be a value of 0, and so this would be your numerator. If someone's in the denominator in group 3, both of their grouping indicators are 0, and so you'd get just e to the beta naught. Canceling, you'd get e to the beta 1. So the way you would interpret this beta 1 parameter is this controls the comparison of risk between someone in group 1 and someone in group 3. This is the comparison for 1 to 3. Likewise, if you compare group 2 to 3, you find out that we get an odds ratio of e to the beta 2. So beta 2 controls group 2 relative to group 3, the group that's left out. And that is typically what you've seen when we have factor variables with a base group that's left out. You always compare to that base group. If you wanted to compare group 1 to 2, you can set this up again. You can have group 1 odds in the numerator, group 2 odds in the denominator, and you'll simplify and you'll get e to the beta naught plus beta 1, e to the beta naught plus beta 2, and you're left with this combination of e to the beta 1 minus beta 2, because the negative beta 2 comes from being down here in the denominator. Comes up reciprocal to a negative power in the numerator with a negative. And so this is a function of both beta 1 and beta 2. So if you want to compare group 1 to group 2, it's a tougher comparison in R, and we can either trick the software to do this, or we can explicitly do this odds ratio. But comparing group 1 to group 2 is a tougher job. Here is such an example with 2 predictors. We've got our pepper rating for faculty again. Remember, pepper equals yes or 1 means the student thought the faculty member was attractive. That's the response. And the predictors are the gender of the faculty member and the area, the subject area where the instructor teaches. And so the choices are humanities, social science, STEM for science, technology, engineering, and math, and pre-professional for professional training. And so you'll notice on this variable we have social science, we have STEM, and we have pre-professional. That means the base comparison level that's been left out is humanities. So on the previous overhead, if we're going to talk about this coefficient right here for STEM, it's a negative coefficient, and this would mean that STEM being the odds of a STEM faculty member being in the numerator of the odds ratio would have lower risk of being a pepper, getting a pepper rating, being attractive according to students, compared to the denominator grouping, which would be humanities. Let's talk about making a logistic regression model that has an interaction term between factor variables. So x1 and x2 are grouping variables, factor variables, and then we're going to have them interact. So just two-level factor variables, 0, 1 for x1 and 0, 1 for x2, and then their product right here, x1 times x2. And so let's think about making an odds ratio for the effect of x1 at a level of x2. We've gone through this kind of thing before, except now our odds logistic regression model function has an interaction in it. And so in the numerator, we're going to put in x1 equals 1. There'll be a 1 here. And in the last part, it's going to be beta 3 times 1 times x2. And so that's why we have beta 3 times 1 times x2 appearing in the numerator. You'll notice in the denominator odds, because x1 is a 0, we of course have x1 as a 0 for the beta 1 times x1 term, but we also get a 0 for this last term because it's beta 3 times 0 times x2. And so that last beta 3 term wipes out. And we're left with, after canceling, an odds ratio that is e to the beta 1 plus beta 3 times x2. And what's interesting about this is that this is an odds ratio for x1. And notice that it is a function of the value of x2. And so this is exactly what interaction means. It means the effect of x1 depends on what the level of x2 is. If the level of x2 really doesn't matter at all, that will happen if beta 3 is 0. It would wipe out this functional dependence on x2, and you'd be left with just e to the beta 1. So beta 3 is an interaction parameter, and it controls the complicated interacting effects of x1 and x2 together on the response. Well, those are the ideas. Now let's get a little bit more specific about doing inference. You can do inference on the beta parameters just like you always have in regression models. You can make a confidence interval for the beta parameters, and if the beta parameters are quite different than 0, all the confidence bounds are above 0 or below 0, you know that this particular term has a significant effect on risk. A confidence boundaries that would contain 0, you would not be able to say that there was a significant effect on risk. You can also do testing of the coefficients. Are coefficients significantly different than a particular value? And of course, p-values that are small would mean that the underlying value of the parameter was significantly different than delta, usually delta 0. And you can do tests for parameters, just like beta parameters, just like you did in all other regression models. And so here is some of our output from the Rate My Professor data. And you will notice that the confidence interval for the beta 1 parameter, beta 1 hat, of course, is negative 0.30228. And when you make a confidence interval out of that data, you get these boundaries right here from confint. That's just saying do the confidence interval for the second component, ignore the first one. Here's the confidence interval. Notice it contains a value of 0, so you'd not be able to conclude that the risk or chance of a pepper rating is different for male or female faculty. Notice that the z statistic over here is given. This would be the beta 1 hat value minus 0 divided by this standard error, and we get something that's almost about -1. The p-value for testing, if this is significantly different than a parameter value of 0, in scientific notation is a p-value of about 0.3385, and again concluding not enough evidence to say that gender differs, that there's an effect of gender on the risk of getting a pepper. Notice the slight difference in inference for gender if we include the field of study for the faculty member. So this top panel up here is for a model that only has the indicator dummy factor variable gender. The second block down here has the field in it as well, an adjusting variable. And notice the confidence interval for gender has slightly adjusted compared to what it is without the field. So there is some slightly different inference given, but not really important. The gender effect is still got a confidence interval containing 0. A lot of times in logistic regression, however, we really don't do inference or report inference on the beta parameters as much as we do inference for odds ratios. So frequently what we'll do is we'll report an odds ratio and a confidence interval for an odds ratio. And remember, odds ratios are e to the beta parameters. We've talked about this one before. Odds of a male faculty member are about 0.74 times the risk of a female faculty member of getting a pepper rating. And you can do a confidence interval for an odds ratio as well. So you can do e to the confidence interval boundaries for the beta parameter, and you'll get the corresponding confidence interval boundaries for the odds ratio. And the difference is that we're looking for whether the confidence interval for the odds ratio is different than 1. We've been training you up till now to worry about confidence intervals differing and containing 0. But on the odds ratio scale, what's important or no effect is 1. And you will notice that this confidence bound starts on a lower boundary that is smaller than 1 and goes to an upper boundary that's greater than 1. And so an odds ratio of 1 is a reasonable thing to say about the population generating these data, and so not enough evidence to rule out a odds ratio of 1 between males and females. In other words, can't rule out the fact that there really could actually be no difference in risk of getting a pepper rating. And so here are the confidence intervals for the simple model. Here is a confidence interval for the gender coefficient from the more complicated adjusting model that has the field of study in it. And notice you get the same inference, that the confidence interval for the odds ratio contains 1, and so therefore not enough evidence to say that there is a gender effect on the risk of a pepper. Now what we're going to do in the next set of lecture notes is talk about how to do interpretations of effects in a complicated model like this one, where we are going to have an effect of a potential effect of the gender of the faculty member and their field of study, but that maybe the gender of the faculty member effect differs depending on the field of study. And so that is a complicated interaction model, and in the next set of notes and presentations we're going to talk about how to do interpretations in odds ratios in a complicated situation like this one. And what you're going to find is that effect plots will help you understand this better, but it's still going to be quite complex, and we're going to take up this discussion in our next set of lecture notes.